Well, hello 403ers. So we are doing, this is our third video, and we're going to take a look at further on stuff with mesh analysis. We're going to look in particular right now at a super mesh. So let's consider a problem a little bit bigger than we did last time, but we'll follow the same basic procedure. We'll set up here where, let's say we have a voltage source, let's say VA, right, plus up here, minus down here, goes around, and let's say I set up on this one, let's say I want a current source, let's say we've used A there, let me use IB as a current source. And got a resistor and a resistor. Maybe I should stick a resistor there too. Maybe we'll come around here, we'll put a resistor down here, and maybe I should put a voltage source here, which is, let's say, VC. So I've got a little circuit, and we'll make this R1, R2, R3, R4, R5, R6. Alright, so the difference between mesh analysis and regular loop analysis, for mesh analysis we're dealing with a planar circuit, which means it can be laid flat here, no wires cross each other. The whole idea of this is that we can draw nice little loops. Let me draw the loops. I did this in blue. Let me draw the loops here in green. So I can say, hey, here is my mesh current I1, and here's the second mesh current I2, and here's another mesh current I3. Now I could not have drawn this as a mesh current around the outside. Mesh currents cannot contain other mesh currents, they can't cross other mesh currents, they must fit in nicely. The whole purpose of that is so that we have a nice consistent way to draw our currents in this, right, which technically are loops, that restrict down so we get the minimum number of equations to describe this. We don't get a lot of redundancy, we don't waste a lot of time, we get a nice efficient area. You know, because there's all kinds of loops. I could have drawn a loop around here, I could have done, you know, a loop like that, right? There's just tons and tons of them. So it's a nice consistent way to draw them, and we get good equations. If you don't have a planar graph though, technically it's not called mesh analysis, you have to go to what's called loop analysis. So people go, oh, you can't do mesh analysis. That's true, you do loop analysis. Not a big deal as it goes on. So this one I made a little more complicated. I have different voltage sources, I have current sources, and so on and so forth. And I deliberately stuck this current source in an area where it's kind of in the middle, so it's a little bit more complicated. It allows us to make what we call a super mesh. And really what's going on here, remember what flows through here is technically I1 minus I2 in the direction of here. Or in this case, IB is going up this way, so, you know, IB is, you know, kind of I2 minus I1. So if you think about this, it's saying in this direction, right, IB flows in that direction. Well, that's got to be equal to I2, right, going in the same direction, minus I1. And it's telling you who's winning. I mean, it's saying the difference between I2 that goes up minus I1 has to be this IB. So I1 and I2 are linked together. So they're not technically one current anymore, so super mesh is a little bit kind of a misnomer, but then again supernode was too, because they had different voltages across them. So we kind of consider this as one big area for writing the voltage drops. But when we write the voltage drops, we have to remember which current we're dealing with. And then we have this one extra equation for currents that go into here. Alright, so let's get to it. Now what we're going to do is we're going to take this and we'll say, wonderful, now we write our areas. I always start lower left, that's my basic rule. So I see VA, it's in the direction of what I want. Going around, I get minus I1, R1, passive element in the direction I'm going. I skip this element. I'm going around the outside. So now I hit minus I2, R4. Right? I'm following my loop. I see minus I2, R6. Following my loop, I now get one that has joint currents, but I don't know what the current relation between them is. So I get minus, and I've got I2 minus I3, which is going in the opposite direction. And then I come around and I hit this one again. We're ignoring that because super mesh. So I've now got I1 going this way minus I3 going the opposite direction. Times R2, and we have reached back our point, so that must be equal to 0. That is the voltage drops around our super mesh. So we've got this equation plus this one. Now we may look at this and we go, well, I got a lot of unknowns here that are stuck in, right? And I'm going to get two equations for two unknowns. Well, two equations for three unknowns, but then we're going to use this one. So let me write the equation for I3 and then we'll substitute in and we'll clean this whole thing up. So again, I pick my lower left-hand corner and I walk my way around. So I see here minus passive element I3 going this way, I1 is going the opposite, that's going through R2, right? Minus passive element I3 minus I2 going opposite direction, right? R5, keep going around, I see this voltage source going the way that I want, right? Coming in the minus, going out the plus, so I get plus VC, and then I see my minus, and I only have I3 going through R3. I've reached back down to my point, so that must be equal to 0. Alright, so what we want to do now is simplify this up a little bit. I'm going to take this top equation, and I'm going to get rid of it. What I'm going to do is I'm going to take I1 to the other side. I'm going to take IB to the other. So I get I1 equals I2 minus IB. So I can remove I1. Now you could have chose to take I2 the other way. I could have done, I2 equals IB plus I1. I don't care, whatever makes you happy. You can substitute in to your heart's content. So I'm just doing this one because that's honestly what I felt like. And I just substitute that in for I1 in any equation where I see I1. Simple enough. So I have two sets of equations, VA minus I1, so I've got I2 minus IB. And remember, IB is a known value, right? And this is times R2, that's R1, top equation. Minus I2, I leave it alone, R4, minus I2, R6, minus I2, minus I3. Right. Ooh, did I forget to write its one? I2 and I3 shared R5. Ooh, horribly bad of me. Okay, R5, and then the last equation, I've got I1 again, so I have to substitute for it, minus, right, and I've got I2 minus IB minus I3 times R2, that has to be equal to 0. Alright, so that's this equation. So now I've taken care of that. Now I take care of this last little bit here, which is minus I3, and I get minus I2 plus IB. I just distribute internally, and that's times R2 minus I3 minus I2 R5 plus VC minus I3 R3 equals 0. Now I just have two equations here in terms of two unknowns, so I end up with RA, which is my matrix of resistances for here. And again, you can kind of note, I can write the lovely little equation around the loop as we go. there are the coupling terms and the non-coupled terms as it goes, and I can add up all those resistances. I also have a slightly bigger area for my voltage sources, because I'm going to have this IB times R1, which is going to look like a voltage source because this I is pumping current into it. So that's going to carry in as well. So we can work through, I2 will be our first column, and so for my I2, I'm going to assume that I take these to the other side, so I'll get R1 that's going on, and I2 is now multiplying R4. Again, the negative sign goes away because I'm taking it to the other side. And again, taken to the other side, minus goes away, I get I2 times R6. Alright, I2 minus sign goes away, taken to the other side, R5. And then I2 minus sign, right, R, and then I get R2 in there. So that's all the ones that multiply I2. Now if you think about this, walk around, I mentioned in the last video, if you walk around here, R1, R4, R6, R5, R2, R1, R4, R6, R5, R2. Some of the resistances around your super mesh, or around your loop as it goes. Then I have the coupling terms, which will deal with the I3s. They should be negative, and you'll notice on each one of these as it goes, because I'm going to take them to the other side as well. Where I3 appears, I have a double negative, but I take it to the other side, so I get a triple negative, which means I have a negative left over. So I'll get minus R5, and I've got, again, double negative, take it to the other side, triple, and so I'll get I3 times R2 also, so I'll get R5 minus, or minus R5 minus R2, and that's the coupling terms. So R2 plus R5 is the coupling negated. That tells you that you should see exactly that down here. If you don't, there's a problem. So I can take on this one, now I'm looking for the coupling with through I2 over here. So I get minus, minus, and an R2 taken to the other side gives me negative R2. And same thing here, minus, minus, and I2, positive taken to the other side, it's negative R5. So indeed, the symmetry holds nicely, and I should just be able to walk around the loop with the rest of them and get R2, R5, and R3. And if I look at it, right, I've got now an I3 that's going on, oops, that's on the previous line. So a single minus I3 taken to there one gives me plus. So I get R2, a single one taken to the other side plus R5, and then a single one taken to the other side gives me a plus R3. So it's exactly that, R2, R5, R3. That's what we call our A matrix, our resistivity matrix. And of course this is multiplying our currents, which are I2 and I3. And that has to be equal to our voltages. On the top one I've got VA, and then anything that's all known. So I've got minus a negative IB, but IB is known. So that means plus IB R1, all known terms. I can leave them there. Oh, this does not have any IBs. This one right there, minus negative, which gives me plus IB R2. So I get plus IB R2. And that's the ones around it. Now you might ask, what on earth do these ones work? Well, since I wrote everything in terms of I2, and I kind of considered that I2 was flowing through here, but I2 isn't the one that's actually flowing through here. Really what I'm dealing with is I1, but I1 is I2 minus IB. So when I use I2 as I1, I'm going to get this difference in currents caused by this one pumping. That current flowing through here will look like an added voltage drop on here. So these are the voltage corrections for me using this substitution. So that's what's going on here, right? The net voltage changes, and you'll notice it's only on I1's loop. So what's on this side over here, right, the V, it's the constant voltage is in here plus the voltage corrections for these two passive elements. So I have the IB on R1 and R2, IB on R1 and R2. Okay, same thing has to happen on the bottom loop as it goes. I do have an element in here that is VC, and I've got a minus RB, or minus IB R2, so I get minus IB R2. Again, it's a minus on this one because, relatively speaking, when the IB is creating the extra current for this one, it's opposite direction for this one. Therefore, it has to be a sign difference. And then I will get, let's see, is there any other IBs? No, there isn't, because that's the only cross term that uses I1. So that's the only one that's going to get the correction factor into it. So this right here is my resistivity matrix, this is my current matrix, and this is the voltage matrix with the corrections for the super mesh. And the corrections will only relate to two terms on the combined super mesh area. Whatever variable you get rid of, if I got rid of I2, right, and I had written this in terms of I1, all the corrections would have been for these. So, you know, it's all based on what you want to pick. Then you just enter this as A, you enter this as B, you know, A / B, and you are done in terms of Scilab or MATLAB. So we've already done that. So I'm considering this one done and happy and wonderful for you. Should be easy to do. Stick the numbers in and get your answers. So hopefully this makes sense, and you have an example you can go back and forth on. So I will see you all in class.